Hello there, beautiful mind. Yes, I'm talking to you, the conscious, thinking person watching this screen right now. Tell me something, how do you know you're real? How do you know that everything around you, this device you're watching, the room you're in, your memories of growing up, your knowledge of the world, how do you know any of it actually exists? What if I told you that there's a terrifying possibility, rooted in real physics and cosmology, that you might just be a momentary flicker in an endless cosmic darkness? A brain that's spontaneously formed out of random particles, complete with artificial memories, imagining a universe that doesn't actually exist? A lonely consciousness that will disappear in the next instant, taking all of reality with it? If that thought sends a shiver down your spine, you're not alone. Today, we're diving deep into one of the most mind-bending ideas to emerge from theoretical physics, the Boltzmann Brain Paradox. This isn't science fiction, this is a real problem that keeps cosmologists up at night, a genuine mystery about the nature of our existence that challenges everything we think we know about reality. Before we begin our descent into this cosmic rabbit hole, if you're fascinated by ideas that challenge the very fabric of reality, do us a favor, hit that like button, subscribe to the channel, and ring the notification bell so you won't miss any of our deep dives into the universe's greatest mysteries. And here's something special we'd love to know. In the comments below, tell us where in the world you're watching from and what time it is for you right now. We're genuinely curious about the diverse community of curious minds we're building here. Now, make yourself comfortable. This is going to be quite a journey. We'll start with the basics of thermodynamics, travel through cosmic time, confront some terrifying philosophical implications, and maybe, just maybe, come out the other side with a new perspective on what it means to exist. Let's begin with a simple question: why does time seem to move forward? Imagine watching a video of a glass shattering on the floor. Now, if I showed you that video playing in reverse, with shards of glass suddenly assembling themselves into a perfect vessel and leaping back onto a table, you'd immediately know something was wrong. The universe has a certain direction to it, what physicists call the arrow of time. But why does time have this inherent directionality? The answer lies in a concept called entropy, and understanding this is absolutely essential to grasping the Boltzmann Brain Paradox. Entropy is essentially a measure of disorder or randomness in a system. The second law of thermodynamics states that in an isolated system, the total entropy can never decrease over time, it can only stay the same or increase. This is why heat flows from hot objects to cold ones, why perfume disperses throughout a room, why ice melts in warm water. All of these processes represent increases in disorder, moves toward higher entropy states. Now, here's where things get interesting. The Austrian physicist Ludwig Boltzmann, back in the 19th century, made a revolutionary realization about entropy. He proposed that entropy is fundamentally statistical in nature. High-entropy states are more probable simply because there are vastly more ways for particles to be arranged randomly than there are for them to be arranged in an ordered pattern. Think of it this way: if you toss a handful of coins, you're far more likely to get a random mix of heads and tails than to get all heads. An ordered state like all heads is possible, but extremely improbable. Similarly, particles randomly moving about are far more likely to end up in a disordered configuration than in an ordered one. This statistical tendency toward disorder is what gives us the arrow of time. Boltzmann's statistical interpretation of thermodynamics was brilliant, but it came with a strange implication that would eventually lead to our paradox. If entropy increase is merely statistical, meaning lower entropy states aren't impossible, just improbable, then occasionally, very rarely, a system should spontaneously fluctuate to a lower entropy state purely by random chance. In our box of gas example, it's extraordinarily unlikely that all those randomly moving particles would suddenly congregate in one corner, but it's not strictly impossible. Given enough time, even the most improbable events should eventually occur. And when we scale this idea up from boxes of gas to the entire cosmos, things get very strange indeed. So, to continue our story, we left off with Ludwig Boltzmann proposing his truly daring solution to the puzzle of our ordered universe. He suggested that our entire cosmos, with all its galaxies, stars, planets, and us, might just be a rare and temporary statistical fluke, a random downward blip in entropy within a much larger, eternal, and almost entirely dead universe. Think about that for a second. It means the Big Bang wasn't necessarily the ultimate beginning of everything, but more like a lucky bounce of the cosmic dice. Our entire history, from the formation of the first elements to the rise of life on Earth, would be nothing more than a beautiful, complex, but ultimately fleeting bubble of order in an endless, calm, and featureless ocean of maximum entropy, what we call heat death. Now, Boltzmann was clever about this. He realized that, of course, most of this larger cosmos would be boring and empty. But we couldn't, find ourselves in those dead regions because there's no one there to observe anything. We find ourselves in this incredibly rare, ordered pocket precisely because it's the kind of place that can give rise to conscious, living observers like us. This line of thinking is now known as the anthropic principle, and Boltzmann's work is one of its very first appearances in modern science. Now, this Boltzmann universe idea was brilliant, but it wasn't without its problems, and other scientists were quick to pounce on them. The mathematician Ernst Zermelo raised a crucial point using something called the Poincaré recurrence theorem, which, in simple terms, suggests that in a closed system, things will eventually return to a state they were in before. Zermelo argued that this made the second law of thermodynamics absolute, not just statistical. But the even bigger problem for Boltzmann's idea came from thinking about the size of fluctuations. If you have an eternity for random fluctuations to happen, then yes, you could get a huge, universe-sized fluctuation like ours. But here's the catch: small fluctuations are exponentially more common and more probable than giant ones. It's far, far easier for randomness to create a single, ordered brain than an entire ordered universe. The astronomer Arthur Eddington and later, the legendary physicist Richard Feynman, drove this point home. They argued that if Boltzmann was right, then the most common kind of conscious observer in the cosmos wouldn't be a person like you or me, living in a coherent universe with a past and future, but rather a much, much smaller fluctuation, perhaps just a lone, self-aware brain with a full set of false memories, spontaneously forming out of the void and then dissolving back into chaos a moment later. This terrifying specter is what we now call the Boltzmann Brain Paradox, and it became the central problem with this line of thinking. Let's just sit with that image for a moment, because it's as strange as it is important. What is a Boltzmann brain, really? Well, over a sufficiently long time, and we're talking about timescales so vast they make the current age of our universe look like a single blink of an eye, random particles bouncing around in the heat death of the universe could, purely by chance, assemble into any structure, no matter how complex. A diamond the size of a planet? Possible, but incredibly unlikely. A copy of the Eiffel Tower? Also possible, but still very complex. The simplest, most likely self-aware structure that could form is a functioning human brain, complete with all the neural pathways and chemistry needed to create a conscious experience, complete with entirely fabricated memories of a life that never actually happened. This brain would pop into existence, convinced it's a real person sitting watching a video about cosmology, and then, an instant later, it would dissolve back into the random chaos from which it came. The reason this is so troubling is that if our cosmos is truly eternal and mostly in a heat-death state, then these disembodied Boltzmann brains should, by the sheer power of statistics, outnumber ordinary, evolved brains like ours by an unimaginable margin. One estimate suggests a Boltzmann brain might form through a quantum fluctuation once every 10^10^50 years, that's a 1 followed by 10 to the power of 50 zeros, a number so colossal it's literally beyond human comprehension. Another estimate for formation via a different process, thermal nucleation in the kind of space we seem to live in, is once every 10^10^69 years. So, if you do the math, these random brains are statistically far more common than we are. This leads to a devastating conclusion: if Boltzmann brains vastly outnumber us, then you and I are statistically much more likely to be Boltzmann brains than we are to be real people in an ordered universe. Every memory you have, every piece of knowledge you possess, every person you love, all of it could be nothing more than an accidental, momentary fabrication in a spontaneously created brain that will cease to exist in the next moment. Now, you might be objecting right now. But that's ridiculous. I know I'm real. I have a consistent life, I have a body, the world follows reliable physical laws. And intuitively, you are absolutely right. But here's the cruel, clever twist of the Boltzmann Brain Paradox: a properly formed Boltzmann brain would have those exact same thoughts and intuitions. If you were a brain that had just fluctuated into existence, you would be equipped with whatever memories and cognitive structures are necessary to make your experiences seem coherent and continuous. You'd remember eating breakfast this morning, you'd know about physics, you'd feel the solidity of the floor beneath your feet, even though none of those things actually exist in an external reality. The scenario suggests that the vast majority of beings who believe they're real people in a real universe are actually these momentary fluctuations, utterly convinced of a reality that doesn't exist. This creates what the physicist Sean Carroll calls cognitive instability. He points out that if we were Boltzmann brains, our reasoning processes and memories would be completely unreliable, since they weren't formed through interaction with a real world but just assembled randomly. This means we couldn't trust any of our conclusions, including the scientific theories that led us to the Boltzmann brain concept in the first place. It's a paradox that eats itself. The theoretical physicist Brian Greene has summed up the feeling of many scientists well, stating, "I am confident that I am not a Boltzmann brain." However, we want our theories to similarly concur that we are not Boltzmann brains, but so far it has proved surprisingly difficult for them to do so. So, where does this leave us? Well, the consensus among modern cosmologists is not that we are actually Boltzmann brains, but rather that the very fact our theories predict we should be Boltzmann brains is a huge red flag that those theories are flawed or incomplete. Sean Carroll has stated plainly, "We're not arguing that Boltzmann brains exist, we're trying to avoid them." The Boltzmann brain problem has become a powerful tool, a kind of reality check for our cosmological models. If a theory of the universe, like certain versions of eternal inflation or a multiverse, predicts that Boltzmann brains should vastly outnumber ordinary observers, most physicists take that as a strong hint that the theory is on the wrong track. This has pushed cosmologists to look for models that naturally avoid this bizarre outcome. Some solutions involve the idea that the universe might not last forever in a state that allows for these fluctuations. For instance, if the vacuum of space is unstable and could decay into a different state within the next 20 billion years or so, that would cut short the infinite time needed for Boltzmann brains to dominate. Others look to a better understanding of quantum mechanics or string theory to provide a way out. The key takeaway is that this isn't just a fun philosophical puzzle, it's a serious problem that shapes how physicists think about the ultimate fate and nature of our cosmos. It forces us to confront deep questions about what it means to be real, what we can truly know, and why we find ourselves in a universe that seems so structured and reliable. It's a reminder that sometimes, the most useful ideas in science aren't the ones we believe are true, but the ones that help us rule out what is almost certainly false. And on that comforting note, we can perhaps rest a little easier, confident that we are, almost certainly, not just brains floating in the void, but genuine inhabitants of a genuinely amazing universe. As cosmological theories evolved throughout the 20th and into the 21st century, Boltzmann's basic insight took on new life, and new terror. Around 2002, some cosmologists began to realize with growing concern that in many theories about the universe, brains that spontaneously form from random fluctuations would vastly outnumber brains that evolved naturally through cosmic history. Let's sit with that implication for a moment. If the universe is incredibly vast, perhaps infinite, and lasts for an incredibly long time, perhaps forever, then even events with astronomically small probabilities become inevitable. Given enough time, random particles will arrange themselves into every possible configuration, including functioning human brains complete with memories and consciousness. These spontaneously generated observers came to be known as Boltzmann brains, or BBs for short, and they represent the ultimate reduction of what's necessary for observation. A Boltzmann brain wouldn't need a body, a planet, a star, or even a universe. It would simply be a self-aware configuration of matter that fluctuates into existence complete with whatever memories, knowledge, and sensory experiences are necessary to make it believe it's a real person living in a real world. Now, here's where the paradox truly bites. If we do the calculations, forming a single functioning brain through random fluctuations is exponentially more probable than forming an entire ordered universe spanning billions of light years. Therefore, in a sufficiently large and long-lasting cosmos, Boltzmann brains should outnumber ordinary observers like us by an unimaginable margin. One estimate suggests a Boltzmann brain might form once every 10 to power 10 to power 50 years through quantum fluctuation, or once every 10 to power 10 to power 69 years through thermal nucleation in a de Sitter space, the kind of universe we seem to inhabit. These numbers are so large they defy comprehension. But if the universe truly lasts forever, then even these astronomically rare events would eventually occur, and would occur infinitely many times. This leads to a devastating statistical conclusion. If Boltzmann brains vastly outnumber ordinary observers, then you and I are statistically much more likely to be Boltzmann brains than we are to be evolved beings in an ordered universe. Every memory you have, every piece of knowledge you possess, every person you love, all of it could be nothing more than an artificial fabrication in a spontaneously created brain that will cease to exist in the next moment. The Boltzmann brain problem isn't just a quirky thought experiment, it has become a serious criterion for evaluating cosmological theories. If a theory predicts that Boltzmann brains should vastly outnumber ordinary observers, many physicists take that as evidence that the theory is likely flawed or incomplete. This has pushed cosmologists to look for models of the universe that avoid the proliferation of these disembodied observers. One class of solutions involves the ultimate fate of the universe. If the universe doesn't last forever in a high-entropy state but instead eventually transitions to something else, that could prevent the formation of Boltzmann brains. For instance, if the vacuum of space is metastable and could decay into a different type of vacuum within the next 20 billion years or so, that would cut short the time available for Boltzmann brains to form. Some hypothetical mechanisms for this include processes involving super-heavy gravitinos or what physicists jokingly call death by Higgs, where the Higgs field triggers a catastrophic phase transition. Another possibility is that our understanding of quantum mechanics needs refinement. Sean Carroll has suggested that a better understanding of the measurement problem in quantum mechanics might show that some vacuum states cannot support any observers at all, including Boltzmann brains. Others have looked to holographic string theory, hoping that a more complete theory of quantum gravity might naturally resolve the paradox. The problem becomes even more complex when we consider theories of eternal inflation and the multiverse. In an infinite multiverse containing all possible universes, the ratio of normal observers to Boltzmann brains depends on how we count, what cosmologists call the measure problem. Choosing different measures can give wildly different answers about whether Boltzmann brains would dominate. Some physicists have taken a more direct approach. Maybe Boltzmann brains simply don't count as valid observers. Quantum fluctuations are easier to exclude than thermally nucleated brains, as we can impose criteria like their lack of sustained interaction with an environment. But this approach remains controversial. If something has the same structure and experiences as a normal brain, what philosophical justification do we have for excluding it from the category of observer? What's particularly interesting is how the scientific community has largely rallied around the need to avoid theories that predict we should be Boltzmann brains. There's a general consensus that such theories are cognitively unstable, they undermine the very reasoning processes we use to develop and believe them. As Carroll puts it, we're not arguing that Boltzmann brains exist, we're trying to avoid them. This practical approach has yielded fruit. By recognizing the Boltzmann brain problem as a serious constraint on cosmological theories, physicists have been able to rule out or modify various models of the universe. The very fact that this paradox has forced such rethinking shows its power as a theoretical tool, despite its bizarre nature. The Boltzmann brain paradox isn't just a physics problem, it's a philosophical earthquake that rattles our understanding of reality, consciousness, and knowledge itself. It connects to age-old questions about how we can know anything about the world beyond our own perceptions. This paradox has echoes in philosophical thought experiments throughout history. The Chinese philosopher Zhuangzi famously wondered whether he was a man who had dreamt he was a butterfly, or a butterfly now dreaming he was a man. The French philosopher Blaise Pascal similarly questioned whether our waking life might be just another form of sleep, slightly different from our nighttime dreams. The Boltzmann brain gives these ancient philosophical puzzles a modern, scientific framing. At its heart, the paradox challenges what philosophers call content externalism, the idea that the meaning of our thoughts is determined by our relationship with an external world. If you're a Boltzmann brain with the same neural configurations as me, do you have genuine thoughts about cosmology, or are you merely having thought-like processes that don't actually refer to anything real? If our memories weren't formed through actual experiences but were just spontaneously generated, can we truly be said to know anything at all? The paradox also raises deep questions about the nature of consciousness itself. If a randomly assembled brain can have the same conscious experiences as an evolved brain, what does that say about the relationship between physical structure and subjective experience? The Boltzmann brain scenario suggests that consciousness might be reducible to the right configuration of particles, regardless of how that configuration came to be, a perspective that aligns with physicalist views of mind but also highlights their strange implications. Some have suggested that the very unease we feel about the Boltzmann brain possibility reveals something important about our intuitive understanding of reality. We trust that our perceptions and memories generally correspond to actual events in the world, and that the universe follows consistent laws. The Boltzmann brain scenario violates these deep-seated assumptions, which may be why it feels so disturbing. Yet despite these philosophical challenges, most of us operate with an unshakable, and probably necessary, belief in the reality of our experiences. As you watch this video, you're almost certainly not questioning whether the device in front of you is real, or whether your memories of the past hour are genuine. This practical engagement with the world may be our best answer to the paradox, not a philosophical refutation, but a lived commitment to the reality of our experiences. Theoretical physicist Seth Lloyd perhaps captured the prevailing attitude best when he dismissed excessive worry about Boltzmann brains with the comment, "They fail the Monty Python test, stop that. That's too silly." A New Scientist journalist summarized this perspective well. The starting point for our understanding of the universe and its behavior is that humans, not disembodied brains, are typical observers. As we bring our exploration to a close, let's revisit the central question: what should we make of the Boltzmann Brain Paradox? Is it a genuine crisis for cosmology, a philosophical curiosity, or something in between? The current consensus among cosmologists is that the prevalence of Boltzmann brains in certain theories signals that those theories are likely missing something important. The fact that our best cosmological models sometimes predict that we should be Boltzmann brains is taken not as evidence that we are Boltzmann brains, but rather that those models need adjustment or replacement. In this sense, the paradox serves as a valuable theoretical tool, a reductio ad absurdum argument that helps physicists refine their understanding of the cosmos. Many physicists believe the solution lies in the fact that our universe hasn't existed for an infinite amount of time. If the universe began a finite time ago with the Big Bang, and will eventually transition to a state that doesn't allow for Boltzmann brain formation, then the paradox might be avoided altogether. The timescales required for spontaneous brain formation are so astronomically large, far exceeding the current age of the universe, that in a finite cosmos, Boltzmann brains might simply never occur. This doesn't entirely resolve the philosophical unease, but it does address the scientific problem. If the universe is both finite in past and future, then the statistical argument that Boltzmann brains should dominate falls apart. We might be left with a cosmos that is genuinely ordered, with a clear arrow of time extending from a low-entropy beginning to a high-entropy end, with no place for spontaneously generated observers to take over the population statistics. As we've seen, research continues on multiple fronts, from quantum gravity to the cosmology of the early universe, to develop models that naturally avoid the Boltzmann brain problem while still accounting for all our cosmological observations. The very active work in this area shows that physicists take the paradox seriously as a theoretical constraint, even as most reject its literal truth. So where does that leave us, here and now, as we contemplate this strange idea? However we resolve the technical aspects of the paradox, the Boltzmann brain invites us to reflect on the extraordinary fact of our existence in an ordered, law-governed universe. The very fact that we can formulate these questions, follow complex chains of reasoning, and develop mathematical descriptions of the cosmos is itself a kind of miracle, whether it's the result of billions of years of evolution or something far stranger. And so we reach the end of our journey through one of the most mind-expanding ideas in all of physics. We've traveled from the statistical mechanics of gases to the ultimate fate of the cosmos, from the thoughts of a 19th-century physicist to the cutting edge of modern cosmology. The Boltzmann brain paradox has taken us to the very edge of what we can know and what we can even coherently imagine. As we part ways, I want to leave you with a final thought. However we resolve the technical aspects of this paradox, it serves as a powerful reminder of the incredible privilege it is to be a conscious being capable of contemplating the cosmos. Whether we're Boltzmann brains or evolved creatures in a vast but finite universe, the fact remains that we're here, now, thinking these thoughts together. The universe, or whatever this is, has produced beings that can look up at the stars and wonder about their place in the grand scheme of things. That capacity for wonder, for questioning, for seeking understanding, that may be the most real thing any of us ever experiences. And on that note, I'll say goodnight to you, wherever you are in the world, whatever time it is for you right now. Thank you for joining me on this strange and wonderful journey. If you've made it this far, you clearly have a beautiful, curious mind, whether it's a Boltzmann brain or not. Don't forget to let us know in the comments where you're watching from and what time it is there. We love seeing our community of curious minds come together from all corners of the globe. Until next time, keep wondering, keep questioning, and may your reality, whatever its ultimate nature, be filled with awe and discovery. Good night, sweet Boltzmann brain, or whatever you are. Good night.